Hello everyone. Today we will see another topic, that is velocity diagram for moving blade of the steam turbine. Here you can see the velocity diagram is same as the hydraulic turbines, except that instead of denoting velocities by V, we are denoting it by C. As we know here, we are using a steam as a working fluid. Both velocity and volume takes part here. So to avoid the confusion, we are using C for velocity and V for volume. So let's discuss all these notations. CB is a blade velocity. C1 is absolute velocity of the steam at inlet. C2 is absolute velocity of the steam at outlet. CW1 and CW2 is whirl velocity at inlet and outlet, which are the component of this C1 and C2, horizontal component of the absolute velocities. CR1 and CR2, these are the relative velocities at inlet and outlet. CF1 and CF2, CF1 and CF2, these are the flow velocity at inlet and outlet, or we can say that these are the vertical component of the absolute velocities C1 and C2. Alpha, exit angle of the nozzle, or the angle which is made by this absolute velocity C1. Theta is the inlet angle of the moving blade. So here this is theta. Phi, outlet angle of the moving blade. So this is phi. Beta is angle made by this C2. That means angle at which steam leaves the moving blade. This steam after moving blade passes over the fixed blade. Hence, we can also say that this beta is the inlet angle for the fixed blade. As fixed blade are not going to move, there will be no relative velocity on it. That means it will enter with the same angle. We know here, when the blades are moving, angle at the inlet is different, while when it glides, when it moves over this blade, at that time it enters with the relative velocity which is at angle theta. This is for moving blade. While if it is a fixed blade, the inlet angle will not change even if when it is gliding over this fixed blade. So this angle will be beta, which is the at which the steam leaves the moving blade, or which is the angle made by the absolute velocity C2. M dot is the mass flow rate of the steam, and K is the blade velocity coefficient, or we can also say it as a friction factor, whose value is equal to CR2 by CR1. Just to remind, this we have done in a hydraulic turbine also, that is VR2 by VR1, friction factor. Once again, here instead of V, we are using C, as steam is a gaseous form of the fluid, and velocity and volume both take parts in a calculation. So to avoid the confusion, volume is denoted by V and velocity is denoted by C. For simplicity, these two velocity triangles are combined together in this diagram. So here you can see this is the outlet velocity triangle, and here it is the inlet velocity triangle. So you can see here, this is CB, C1, and you can see alpha is the angle between the CB and C1. So this is the angle alpha. Component of C1 is CW1. So you can see here also CW1, and another component is CF1. So this is the vertical component, that is CF1. And here you can see from the other end of the CB, okay, this is the first end, this is the another end. So this is the first end, this is the another end. From the first end there is a C1, and from the other end there is a CR1. You can see here also CR1. So this is what the inlet velocity triangle is. Now in a combined velocity triangle, CB is kept same, and from this end, one of the end, you can see here from one of the end there is CR2. So here it is CR2, and from the another end there is C2. So this is C2. C2 has again two components, that is CW2 and CF2. So this is what the combined velocity diagram is. This diagram is mostly used when construction method is used for solving the numerical. As steam turbine also works on the impulse momentum principle, here the work done power will be in this way. So if we apply the impulse momentum principle, the force will be equal to m dot CW1 plus or minus CW2. From combined velocity triangle, we can see here F2C gives you CW1 plus CW2, or even if the direction of this CW2 changes, it will be on the another side, so it will give you CW1 minus CW2. So this F2C will be helpful to find the force. So instead of writing CW1 plus CW2, we can write it simply as CW, that is equal to CW1 plus CW2, or based on the direction of CW2, that is CW1 minus CW2. So we can write here m dot into CW. The work done will be equal to m dot into CW into CB, that is, or you may remember it as U. If you want to find the power developed in a kilowatt, we can write it as m dot CW CB by 1000. It will be in a kilowatt. In case of steam turbine, there are two different efficiencies. First one is a diagram efficiency, or it is also known as a blade efficiency. This diagram efficiency or blade efficiency, it is based on our velocity diagram. That means blade efficiency will be equal to work done on the blades, moving blades, to the kinetic energy supplied to moving blade. Here for now we are talking about the impulse turbine. So we can write here work done for the moving blade is this one. So m dot CB into CW divided by m dot into C1 square by 2. So rearrange it. So twice CW by CB divided by C1 square. This will give you the blade efficiency. The another efficiency is stage efficiency. In previous video, we have seen what is meant by the one stage. For impulse turbine, one stage means ring of nozzle plus ring of moving blade. So the stage efficiency will be equal to work done on moving blade which is the output of that particular stage to the energy supplied per stage. Now work done on the moving blade, it is equal to m dot Cw Cb divided by energy supplied per stage. As we know here, the first ring is of nozzle and after that the next ring is of the moving blade. This is nozzle and this is the moving blade. So here the energy, it is in the form of enthalpy, that is heat energy. So the energy supplied per stage will correspond to the isentropic heat drop. That means delta H into 1000. This 1000 is basically because from the steam table we will get the value of this enthalpy in terms of the kilojoule. This delta H is in kilojoule, but from steam turbine we will from steam table we will get this enthalpy as a kilojoule per kg. So the formula will be Cw m dot Cw Cb by m dot into delta H into 1000, or we can write it as Cw Cb upon delta H into 1000. So this will give you the stage efficiency, that is for the combined nozzle ring and the moving blade ring. So here you can see, here is the ring of the nozzle and after that there is a ring of the moving blade. Here we know that we are having the high pressure, so it will be having H1, let's say, energy, and that H1 will be converted into the kinetic energy. So here it is H2, and difference between it will give you the energy which is supplied towards this whole stage, and that energy we are trying to convert into work done. So here we will get work done and remaining energy will be sent to the next stage, or we can say it is a loss for that particular stage. So this is the output, that is work done, and the difference between this will give you the input or the energy supplied to the particular stage. Let's take a small numerical based on the theorem. An impulse turbine has three similar stages of same mean diameter in geometry. Each stage develops 500 kilowatt. The peripheral speed of the rotor blade at the mean diameter is 100 meter per second. So here we can see there are three stages given, and the power developed in each stage is 500 kilowatt. The mean peripheral speed of the rotor at the mean diameter is 100 meter per second. That means CB is given as 100 meter per second. The whirl component of the absolute velocity at entry and exit of the rotor are Cy2 200 meter per second and Cy3 0 respectively. Don't get confused by Y. Here it is directly mentioned that it is a whirl component at entry and exit respectively. So this will be CW1, that is 200 meter per second, and this one is a CW2, that is 0. The nozzle angle at the exit are equal to alpha to 65 degree. Again, this is given for the stage number 2. So, but mentioned that it is a nozzle angle at the exit. So, it is simply alpha as 65 degree. The steam at exit of the first stage has P2. So here it is given that P2 pressure is given as 8 bar at the exit of the first stage, and the temperature is also given as 200 degrees Celsius. Determined for the first stage. So by considering that these all are for the first stage, what is supposed to find? First one is mean diameter of the stage, that is dm, when rpm is given as 3000 rpm. Mass flow rate of the steam, so m dot. Next one is isentropic enthalpy drop, that means delta H I when the nozzle efficiency is given as 69%. Rotor blade angle, so the rotor blade angles are theta and phi. And last one is blade height of the nozzle, means blade height for the fixed blade and the rotor blade at the exit, that means H we are supposed to find. Let's draw the velocity triangle for this given data. As here CW2 is 0, that means this is CB, here is the CB, and this total distance will be CW1. CW2 is 0 means beta is equal to 90 degree. Now these are the given data, and let's start for the first one, that is mean diameter of the stage. That is dm. So mean diameter of the stage, that means you can find it from the CB. So what is CB? CB is equal to pi dmn upon 60. Don't get confused from where this formula has come. This is u, so u is equal to pi dn upon 60. So same formula is used over here. Now if we put all these values over here, we will get dm equal to 0.6366 meter. Let's go for the second one, that is m dot. Now for m dot, we can see here power is given to us. So by formula, that is power is equal to m dot Cw Cb. We can see here Cw, that means Cw1 plus Cw2. It is given. Cb is also known to us. Power is also given to us in kilowatts. So we can put the values over here, that is 500 into 10 raised to 3 is equal to m dot Cw is equal to 200 into 100. So from here we will get m dot equal to 25 kg per second. Now let's go for the next one, that is isentropic enthalpy drop. So let's say this is the nozzle which is insulated, and it is expected that the steam which is having a heat pass through this nozzle, and high pressure will be converted into the kinetic energy, change in the enthalpy. So that is what known as the isenthalpic process. If we draw that process, isentropic process, on HS diagram. So let's say these are the pressure lines. This is the pressure at the inlet, so P1, and this is for P2. This is only for nozzle. Now don't consider this one. These are for the moving blade. So it is expected for nozzle that the pressure drop inside the nozzle should be isentropic process. So it should follow this from 1 to 2 dash. But actually or practically it will not follow this one. Instead of that, it will follow this actual process, that is from 1 to 2. As we can see here, expected enthalpy drop is from H1 to H2 dash, but what we are getting, the drop in the enthalpy is from H1 to H2. So the efficiency, nozzle efficiency, it is equal to the actual enthalpy drop to the isentropic enthalpy drop. Here you can see nozzle efficiency is given to us as 69%. Now the question is how to find this delta H, that is actual enthalpy drop. We have also seen one formula, that is velocity at the inlet of the moving blade. So C1, it is equal to 44.7 under root of delta H, or it is equal to under root of 2 into 1000 into actual enthalpy drop. So if we rearrange this equation for delta H and put in this equation, we will get nozzle efficiency equal to C1 square by 2 into 1000 divided by isentropic enthalpy drop. Now how to find this C1? So we can find the C1 from the velocity triangle. For that, alpha is given to us and Cw is also given to us. So we can write C1 is equal to Cw1 upon cos of alpha. So 200 divided by cos of 65 degree, and we will get C1 as 473.24 meter per second. Now let's put all these values in this one and find the isentropic enthalpy drop. we will get isentropic enthalpy as 162.3 kilojoule per kg. Next one is to find theta and phi. This we can find from the velocity triangle. So for theta we can see here if CF will be known to us, then theta can be found. So for CF1, alpha and C1 is now known to us. So C1 sin of alpha, and from here we will get CF1 as 428.9 meter per second. Now theta is equal to tan inverse of CF1 upon CW1 minus CB, and from here we will get theta equal to 76.88 degree. Similarly for phi, considering that friction factor is equal to 1, that means CR1 is equal to CR2, which will be equal to under root of CF1 square minus CW1 minus CB bracket square. So from here we will get CR1 equal to 440.4 meter per second. Now as CR2 is known to us and CB is known to us, we can find phi by using phi is equal to cos inverse of CB by CR2, and from here we will get phi as 76.88 degree. Now next one is to find the height of the blade. So H. For that, let's see the cross section of the steam turbine. So here is the shaft, and over which these are the blade. So we can see here, if we are considering this as the D1, let's say inner diameter as D1 and outer diameter as D2. For mass flow rate, we can write rho A into CF1. Here, as it is a steam, instead of rho we have to write the specific volume. So for the given conditions, so here you can see given conditions are that at the exit it is the pressure is 8 bar and temperature is 200 degrees centigrade. So for exit we have to write it as area into CF2 because it is exit condition, and the specific volume at the exit. Now let's see for the area first, then we will move to the another part. Now the steam is passing through this area except this one, idle one. This area, okay, and this area is equal to pi by 4 d2 square minus d1 square, or we can expand this as pi by 4 d2 minus d1 into d2 plus d1. Let's split this 4 also. So pi d2 minus d1 by 2 d2 plus d1 by 2. Now from here you can see d2 plus d1 plus d2 by 2 means this is a mean diameter, and d2 minus d1 by 2, that means this total d2 minus d1, that means remaining distance, that is this and this, and these are the height, and as we are dividing it by 2, so it will be only h, so this is equal to the height. So we can write this as pi into h dm. So our formula for the mass flow rate will be equal to pi dm into h cf2 into specific volume at the exit. Now here we can see theta and phi both are same. Also CR2 and CR1 both are same. So due to that we can see here CF1 and CF2 will also be equal to, they both will also be same. So CF1 equal to CF2 equal to 428.9 meter per second. Now for specific volume we have to use the steam table. Given conditions are P2 is 8 bar and T2 is 200 degrees Celsius. So for these conditions the specific volume is equal to 0.261 meter cube per kg. Now m dot is equal to pi dmh into cf2 upon this specific volume. As m dot is now known to us, that is 25, so pi dm also we have found as 0.636 into h into cf2 is 428.9 divided by 0.261. From here we will get the height as 7.61 into 10 raised to minus 3 meter, or we can write it as 0.6761 centimeter. So this is how we can find the height for the turbine blades. Now let's see the another numerical. A single stage turbine is supplied with a steam at 4 bar and 160 degrees centigrade, and it is exhausted at condenser pressure of 0.15 bar. So here it is given that inlet pressure, that is P1, is equal to 4 bar. So inlet conditions are given to us as pressure 4 bar and temperature 160 degrees Celsius, and the exit pressure, that is P2, is given as 0.15 bar. So m dot is given as 60 kg per minute, that means 1 kg per second. The steam expands in nozzle with the efficiency of 90%. So nozzle efficiency is given as 90%. The blade speed is 250 meter per second. So CB is given as 250 meter per second. Nozzles are inclined at 20 degree. That means alpha is given as 20 degree to the plane of the wheel. The blade angle at the exit of the moving blade is 30 degree. So exit blade angle is 30 degree. Neglect the frictional losses in the moving blade. That means K is supposed to be 1. Determine first one as steam jet velocity, that means C1, that is inlet, absolute inlet velocity of the steam. Second one is power developed. Third, blade efficiency, and last one is the stage efficiency. Let's draw the velocity triangle for this. As inlet and exit conditions are given, so from the Monar diagram we can find the isentropic enthalpy drop. So here is the inlet condition, that is pressure 4 bar and temperature 160 degrees Celsius, and here is the outlet condition, that is 0.15 bar. If we draw for isentropic line, if we draw the isentropic line between these two conditions, we will get the enthalpy drop is equal to 513 kilojoule per kg. So delta H I is equal to 513 kilojoule per kg. Now for C1 we have to find the actual enthalpy drop. So for actual enthalpy drop, it will be equal to nozzle efficiency into isentropic heat drop. Nozzle efficiency is 90%, so 2.9 into 513, and we will get the actual enthalpy drop as 461.7 kilojoule per kg. Now C1 is equal to 44.7 and the root of delta H. If we put the value of delta H over here, we will get C1 as 960.5 meter per second. Now next one is to find the power. Power is equal to m dot CW CB upon 1000. M dot is known to us, CB is also given to us. So the question is to find the CW. Now for CW, we can use this velocity triangle and solve it by the trigonometry also. Let me explain it to you in short. CW is equal to CW1 plus CW2. For CW1, we have C1 and alpha, so we can find CW1 is equal to C1 cos of alpha, and from here we can find CW1. For CW2, phi is given to us and K is also given to us as 1. So first we have to find CR1 from this inlet velocity triangle, that is CR1 is equal to under root of CF1 plus CW1 minus CB. CF1 we can find from C1 and alpha, so we can find CR1 from here, and which will be equal to CR2. Once we have found the CR2, we can find this total, that is CW2 plus CB. So CW2 is equal to CR2 cos of phi minus CB. From here we can find CW2, and we can put this CW, that is CW1 plus CW2 in this equation, and we can find the power. There is another method, that is the construction method. Let's see that. Let's see the construction method. So here from the numerical it is given that CB is equal to 250 meter per second, alpha is 20 degree, phi is 30 degree. From here we can see CR1 equal to CR2 and C1 is equal to 960.5 meter per second. Now as we can't draw 250 meter per second, let's scale it. 100 meter per second is equal to 1 centimeter. So here let's draw a CB of 250 meter per second, that means 2.5 centimeter. So this is CB 2.5 centimeter. Let me extend it for CW. Now alpha is 20 degree and phi is 30 degree. If we recall the combined velocity triangle, it is something like this. So this will help to get the actual diagram. Now we have drawn the CB with a given scale, that is 2.5 meter per second. Now let's mark alpha and phi. So this is alpha and phi. So from this end it will be alpha and from this end will be the phi. So phi is 20 degree and theta is 30 degree. Now on alpha we are having C1. So C1 is 960.5 meter per second. If we use the scale, it will be 9.6 approximately. So 9.6 centimeter. So this will be the C1. Now from C1 we can see, if we draw a perpendicular, you will get the CF1. So simply draw a perpendicular line from this point to extended CB. Let's extend it further so that we will get the complete CW1. Now you can see this other end of the CB is joined to here to get the CR1. So join it so that we will get CR1. Now as K is equal to 1, that means CR1 will be equal to CR2. So let's measure this CR1 and mark it on the phi. So here we can see CR1 is 7.3. So let's mark. CR1 as 7.3. Now again similarly you can see from this point, if we draw perpendicular, we will get the CF2. Now again join this so that we will get CW2. If we join this, we will get C2. This is how we can draw the combined velocity triangle. So let's give the naming. Now we need this total distance for CW. So let's measure it. This is equal to 12.8. So here CW is equal to 12.8 centimeter. That means 1280 meter per second. So let's put all the values in this equation and we will get the power as 320 kilowatt. Next one is the blade efficiency. So blade efficiency is equal to twice of CW CB upon C1 square. CW is known to us now, CB is known to us, C1 is also known to us. Let's put and we will get the value of blade efficiency as 69.37%. Similarly, we can find the stage efficiency. So stage efficiency is equal to CW CB upon isentropic enthalpy drop. That is what we have supplied to the whole stage into 1000, and we will get the value as 62.37%. So this is the another method, that is the construction method to solve the velocity diagram in a steam turbine.